This video is about characterizing Schmitt trigger inverter. It corresponds to section 17.4.1 of Applied Analog Electronics. Okay. The basic idea is to set up a function generator to sweep the input voltage up and down, and then to look at the output and the input voltage both with Characterizing recording system. So we just have a simple wiring setup. We've got TCLC here that's got Characterizing installed. We've got the 74HC14N Schmitt trigger chip here. The highest pin, pin 14, is connected to power. The pin 7 is connected to ground. And you can see there's a little notch on the end of the chip here, and that indicates which end is pins 1 and 14. That notch, incidentally, I like to have it lined up so it's oriented the same way as the TCLC. Just makes it easier to debug if everybody lines their chips up the same way. Okay, and then I've got one of the pins, an input pin, hooked up to the Analog Discovery 2 function generator, the yellow wire here. I've got a black wire that hooks up the ground to the ground, so that the Analog Discovery 2 and the Characterizing system are both using the same ground voltage. I'm powering the chip off of the TCLC's regulated power supply. In addition to hooking up two analog channels here, A0 and A1, I've also hooked up a digital channel to the output. And that's so we can look at the output either as an analog value or as a digital value. Okay, I set up the waveform generator. Here I've got it set up to be a sine wave. The shape doesn't matter all that much. Sine wave is nice that it doesn't have any glitches in it. I'm doing it here at 10 hertz. And I've got an amplitude of 1.5 volts. That means plus or minus 1.5 volts from the offset. And that offset here, I've got 1.65 volts. So the lowest voltage I do is 0.15 volts, and the highest voltage I do is 3.15 volts. That keeps it within the 0 to 3.3 volt range of the chip for the TCLC power supply. And for the TCLC analog to digital converter to work, we have to have all our voltages within that range. And since that's now in a safe range, I can start running it. And I'm running it at 10 hertz, and that's not what I recommended in the book. We'll take a look at what to do about that in a moment. All right, so now let's go over to running Characterizing. All right, so what I'm going to do, I'm in the correct directory here to be able to just say -DAQ, and that should find the TC board there. Go. And let's make this a little bit bigger so you can see what's going on. All right, I'm going to need to add some channels, and I said I had channel A0 and A1 used, so I'll both of those. I should actually label these things. A0 was the input, and A1 was hooked up to the output. And I had one digital channel as well, so I'll add one more channel. It's not an analog channel, but a digital one, and I think for this one I used D10. All right, so those are the signals. Now my input signal was at about 10 hertz, so if I sample at 10 hertz, I'm not going to really see anything. So sample at 100 hertz. And let's just see whether or not this is working. Okay, you can see that I've got a sine wave moving up and down there on the input, and the output is a square wave. There's a problem, though, in that it is going by very fast, and what I'm trying to figure out is where does that square wave change its value? Where does it change from 0 to 1 or from 1 to 0? And if I'm doing this thing at 10 hertz, I'm sampling at 100, so I'm only seeing 10 voltage values. That's not going to give me much precision. So I could go back to waveforms and say, 10 hertz isn't right. Let's do it maybe at 1/10 of a hertz. And now if we go back to looking at what's going on in Teradek, we can see we've got a much slower moving thing, and we've got a chance of seeing where the transition occurs. The trouble is we're still only sampling this 1,000 times in a waveform because it's 100 times a second and it's taking 10 seconds for each period. And trying to find that, okay, the 1 out of 1,000 of those numbers is the one we want. What's the voltage when we make the transition? Finding that number in your file is a little bit of a pain, and you're recording a hell of a lot of data that really doesn't tell you anything because you've got one number out of every 1,000 that's worth something. So there's a way we can get around this thing. Pause this and clear the data. Okay, we don't really need that whole waveform. We just want one value from it. So instead of doing this timed input here and saying sample this 100 times a second, what we can say is only sample it when there's a pin that changes, a digital pin. In fact, what we want to do is sample it only when that pin D10 that we had the output hooked up to changes. So we're saying when the output D10 rises, then record the voltage. Just record it only at those times. Don't record all the other times because we only care about when does that rising happen. Or we also care about when does the falling happen. We'll do that as a separate recording. So let's try running this. Now you notice that nothing seems to be happening. And that's because it's only going to record one value every 10 seconds. And it's recorded one so far. In fact, you can take a look at the number that's recorded right here. It says it's recorded one value. And it said it was at about 1.119. Now it's done two values. It's taken as reporting both the average and the standard deviation of those values. It's also reporting what the output value is here. And the output value, 3.3033, is the average value, and that's also, you can see standard deviation on that too. When we look at the digital value, it's either 0 or 1, and it's always going to record a 1 because it's only making the recording after it's seen the transition from low to high. So once it sees that transition, it records the voltage. And you might want to do this thing until you've got like 10 values, something like that. So you've got a nice average of your values, and you'll know both what the average value of your threshold is and the standard deviation. Okay, and once you've done this, you can say that this is, well, it's doing it 74 HC14N. No, that doesn't look like 74. Okay, and you can put any notes in here about what your setup is, which one of the ones on your chip it was. Some of the information that you'll want is already recorded automatically by Teradek. For instance, over here, it's telling you the supply voltage. It'll also put that in your output file when you finally get around to saving the data. Okay, we've got 10 there, so I think that's enough that we can save that. And I'm going to save this one as output rising, because that's what I triggered on. And now I've got a data file that's got all this information in it. It's got the individual 10 recordings it's got what the power supply voltage was, it's got the average and standard deviation. So basically all the information that's here on the screen, plus a lot more, is there in that file. And it's only got 10 data points. I can clear this and do the similar recording for falling. And we would expect to see a higher voltage for this because remember this is an inverter, and so the output is going to go low when the input crosses the higher threshold. So as we can see, that's now looking like about 1.9 volts, and the other one was about 1.1 volts, I think, something like that. You're going to get different numbers. These parts are not that repeatable, and the power supply voltages from the TCLCs are not that repeatable, so everybody should get slightly different numbers here, but not enormously different ones. You expect to have a higher voltage threshold here. The hysteresis voltage, the difference between the two thresholds, is a little bit better controlled than the individual voltages, so you will see probably about 0.7 something, 0.8 volts difference between the two voltages. And again, you might want to record this for a while so that you get, 10 or so readings. I've got 7 so far. I'll wait another 30 seconds, and I should have another 3 out there. Notice that the output voltage here is now very close to 0. One thing you'll notice when you do recordings with the TeensCLC is the analog to digital converter has a little trouble right at 0 and right at 3.3 volts. The very ends of the range, it can't always get all the way to the end. And so you will often see numbers that may be accurate, maybe not accurate. It's hard to tell. The instrument just isn't that good right at the ends of its range. So I wouldn't trust this DC value being 22 microvolts all that much. It could be anywhere from 0 to 60 microvolts, and the instrument really can't tell. Same thing for when we were looking at the voltage we were seeing before, where it was a few microvolts below what the power supply voltage should have been. It might have been. It might have been that that's measurement error again. And here I've taken more than 30 seconds, so I can save this, and not as rising, but as falling. And I've got the 2 data files. I can look at them. I can record the data. It's actually quite simple on this one to do characterizing of a Schmitt trigger, because the triggering here makes it very easy to say, this is when I want to look at the data, and it just records only the data you're interested in. You don't have to try and extract it from a large recording. That's about all there is to characterizing the Schmitt trigger.